Good afternoon, everyone. Okay, thank you. My name is Gladue. I'm with a US-based company called MECO. This is my colleague and friend, Arthur Billon. He's from our sister company, Eurowater, based in Denmark. The reason we're here today is to talk with you a bit about the critical water utility needs for green hydrogen production. What we'll do is we'll go through some of the general rules of thumbs about capacity requirements for this process. And then Arthur will follow with a discussion on the quality requirements and some case studies for this particular application. And the goal here is for us to just generally collaborate so that we're continuously optimizing the standardization of solutions for green hydrogen production, share some information with you about our experience in that space, and certainly we appreciate any questions that you have as well. So just a little bit of background about our organizations for context. MECO is founded 95 years ago. It is a US-based company in the New Orleans area in Mandeville, Louisiana on the north shore of Lake Pontchartrain. We also have offices in Ireland, Singapore, and the United Arab Emirates. Over 350 employees, roughly 10% of those are veterans. And the industries that we serve, oil and gas, biopharma, energy, and we've got 27 patents in water purification. Company was recently acquired by Grundfos, a Danish-based pump manufacturer. Eurowater was acquired a few years prior to us. Eurowater has been involved in the green hydrogen market, developing standardized solutions for about 8 years since 2015. This is a new market for MECO, given, of course, where the United States is with adoption of green hydrogen production. So that's why we're here together to talk with you. So first off to start, the question is begged is why is there no power to X without ultrapure water, right? And what we're talking about in the context of power to X is the ability to reuse excess sustainable energy for production of other sustainable energies, in this case, green hydrogen. Now, of course, that's going to beg the question for United States application. We're still very much dependent on fossil fuel generation for electricity, so that's another work in progress. But with regard to the actual process of green hydrogen production, not using fossil fuels as feedstock, that is what we can talk about in that context as we work towards those more sustainable electricity sources elsewhere as well, right? And so there's a lot of ideas about what hydrogen should be used for, right? But there's already a lot of hydrogen that's being used currently for fertilizer production in refineries. The bulk of this, though, is coming from gray hydrogen processes, right? So that it's being sourced from natural gas, fossil energy, and the carbon is not captured in gray hydrogen production, right? So the question then becomes, if we use that as our baseline for comparison of what the current needs are, not even factoring in growth applications for it, right? How much electrolyzer capacity then will be needed for us to produce the amount of hydrogen that we're already using today as gray hydrogen? And then how much water do we need to feed the electrolyzers with? Because remember, in green hydrogen, we're talking about water as the feedstock here to that process as opposed to fossil fuels, okay? And then that also begs the question from a purity requirement, because there's different electrolyzer technologies, and they're going to have various requirements and limitations with regard to the water quality that's necessary to ensure the integrity of the process. Okay? So to answer that question of how much green hydrogen capacity do we need to just replace the existing gray hydrogen capacity, that's about over 1,100 gigawatts of capacity. Okay? That is a lot of power. And then so far as the ultrapure water needed to feed the electrolyzers of that capacity, we're talking about roughly 207,000 cubic meters per hour. That's about 54.7 million gallons per hour, or about a little over 1 billion cubic meters per year, which is about 273 billion gallons per year. It's a lot of water. That's the bottom line, okay? That's a lot of feedstock that's necessary. And we'll touch on this a little bit, but one of the questions that has come up recurringly through the last couple of days is, well, what about variable feed water sources, right? Because water itself is a precious resource, right? Can we use seawater? Can we reuse recovered wastewater? And so there's some complexities to those variabilities. Anything can be done, but it becomes the question of the economics and the technical feasibility and reliability, right? So in comparison to those figures, right, from an overall goal standpoint, we talked about needing over 1,100 gigawatts of capacity. The EU only has a target of about 50 gigawatts of capacity by 2030, and the US, according to the roadmap that was mentioned earlier, has loftily suggested goals of about 50 gigawatts by 2050. So these goals are nowhere near aligned with the current gray hydrogen demand that's even there with regard to green hydrogen replacement, okay? So water treatment for green hydrogen, right? How much do we really need when we start talking about the modular sizes that are typically found in these electrolyzer plants, right? And so in defining any solution for water treatment, we tend to start with asking those basic questions of quantity and quality. What quality of water do you need and how much of it do you need? And then you can design the system based around those understandings, right? So as a general rule of thumb here, you know, what we're looking at here is for ultrapure water conversion to hydrogen, roughly 9 kilograms of ultrapure water will yield 1 kilogram of hydrogen. What that equates to in gallons is about, for just shy of 2,000 US gallons, you get roughly a metric ton of hydrogen. So about 1,954 US gallons will get you about 1 metric ton of hydrogen. And then from an electrolyzer capacity standpoint, what we're looking at is roughly 200 liters per hour is required for every 1 megawatt of capacity. And for gallons per minute, that's just shy of a gallon a minute, okay? So about 0.88 gallons per minute. It's really not a lot of water per megawatt when you factor it in that context. Now, in contrast to that, right, what we're also looking at here, as I mentioned, is there's different water sources that might be considered. Okay, and so that factors into the overall cost and the energy requirements that are necessary. Because remember, power to X, we're talking about bringing in excess renewable energy that might be there from solar, you know, wind, hydroelectric and whatnot. But how much do you need depending on your feed water source? So as this recurring question has come up repeatedly over the last couple of days, well, what about seawater? Can you do it with seawater? Of course you can. However, there's more power required. The systems become far more costly and complex because there's more variability and the source water is more challenging, so there's an increased capital cost. And your yields, what we call recovery rate in these systems, reduces as your water becomes more challenging. So as you see here, right, with groundwater, that's like well water. It's very stable, it's not subject to seasonal variations and things like that. It's very easy to treat, relatively speaking, okay? That you'll get roughly 71% recovery, 75% recovery, somewhere in that regard. In the comparison, what you see is you get a cubic meter of ultrapure water for every 1.4 cubic meters of raw groundwater that you might need. From there, right, we look at treated wastewater or brackish water, for example. There's a lot more variability, and you can count on getting less ultrapure water. So that same 1 cubic meter is going to require more like, you know, what is it, 1.5 cubic meters, so you go down to about 66%, and that's similarly the same for surface water. Seawater is the question that has come up the most, and we're talking about recovery rates of roughly 30% at that point, right? So what that means is for every cubic meter of water you put in, you're only gonna get 1/3 of a cubic meter of pure water out. And the energy and pumping requirements increase, and the scale of the system has also increased. So pumping requirements for green hydrogen, in contrast, right? We've got to think about the total cost of operation with regard to these systems. And it's common to conflate the pumping requirements with regard to the overall cost and energy demand of water treatment. In reality, the pumping requirements should be carved out and considered separately because the ultrapure water demands for makeup are relatively minuscule in that context, okay? So ultrapure water generation generally only represents about 1% of total cost of operation for the system, whereas with the pumping requirements, that could easily be 10 to 20% because we're talking many orders of magnitude of flow rate for recirculation and continuous polishing within this process. And then there's just a little bit of attrition where you have to have fresh makeup, and so that ultrapure water generation is relatively small compared to the actual recirculation and pumping requirements. So it's very important that when people talk about water treatment representing some large percentage of the total cost of operation of electrolyzer, it's very important to ask that question. Well, are you talking about pumping in that as well and recirculation, or are you talking about only the generation of the ultrapure water and makeup itself? And that's a very, very, very important delineation once you break it down in that context. So just a little bit of an example of this, with regard to the pumping requirements. The ultrapure water requirements for pumping are relatively small. You need a pump to get it through the water purification equipment. And typically, it's going to be a reverse osmosis system with some sort of deionization, polishing, and whatnot. But the recirculation, there's a whole number of other recirculation requirements. Polishing loop, the main loop, cooling water loop, and there's high flow rates, and these are continuous flows as well. So you can see how that might change dramatically. And so how much pump capacity in all reality, right? And this just kind of illustrates that point a little bit more clearly, right? So for feed water, you might only need 200 liters per hour for a 1 megawatt electrolyzer node, and you might need 50 to 100 cubic meters per hour of recirculation capacity in the rest of the pumps downstream of that. So a very, very significant difference. It's all critical, it's all very, very important parts of the process, but it's important to understand that with regard to evaluating total cost of operation, and that the actual generation of ultrapure water is relatively small in comparison with the pumping and recirculation requirements that are there. And the last thing that I'll mention here before I turn it over to my friend Arthur to tell you a little bit more about the quality requirements and some of the case studies that Eurowater has engaged in their time servicing the green hydrogen market. I will mention that pump selection is of critical importance, and this is a little bit of a crossover to that quality discussion, because leachability of materials of construction is very, very important. When you're dealing with ultrapure water, it can pull materials out of lesser, it can pull contaminants out of lesser materials. So it's very important to use austenitic stainless steels like 316L, 316 titanium alloys, or even composite materials to ensure that there's no contaminants pulled from the piping systems that may in turn foul or damage the electrolyzers. So that is very, very critical. And with that, I will turn it over to my friend Arthur to tell you a little bit more about the quality requirements and case studies.
Great. Thank you.
Certainly, thank you.
Good. Can everyone hear me quite well? Great. So now we know what we start from. So we know how much water we need. We also know where it comes from. And we're going to switch now to the quality, which is like damn important for this application because it can affect performances, the length of life of the materials, and so on. But before switching to that, let's just go back to who we are, because now we have had the presentation of MECO, and we are Eurowater, a European-based company. We have been in the business since 1936 in water treatment. And long story short, we have like 23 offices over 14 countries and distributor over 18 countries. So this is the global market we are covering. Hydrogen-wise, in numbers, we have had like over 80 plants delivered to this day, which more than 40 of them are covering 1 to 5 megawatt system, which are containerized PEM solutions. In other numbers, megawatt talking, we have covered a bit less than 300 megawatt with those systems. So this is just to give you an idea of how we built this experience over the last 8 years, approximately. And from these years of experience and all these systems that we have set in operation, we could develop some kind of rule of thumbs regarding flows, as Aaron just mentioned, the origin of water, but also quality. So now we summed up. We know where it comes from. We know the flows. What about the quality? With all those systems, we have covered two main range or two main types of electrolyzers, which are like full-scale developed to this day, which are alkaline electrolysis and PEM, an advanced alkaline or high-pressure alkaline system, which we divided in those two categories. The reason why is because they have slightly different needs in terms of water quality. The needs in flow are the same, but the quality-wise, it can change. It can change why? Depending on the type of electrolyzer, it can impact. Depending on the electrode material itself, depending on the brand of the electrolyzer itself, it can really differ from a brand to the other. And the reason why is because each dissolved ion or each component that can be found in the water can have a destructive impact on these technologies. So we have shown some example of it, but basically the rule of thumbs are, for alkaline systems, we will need, in 99% of the cases, below 1 microsiemens. This is how you measure the quality of the water, which is the conductivity. For PEM and advanced alkaline systems, it's much stronger requirements, so we need always below 0.1 microsiemens. There are other aspects that we can look at, such as silica, which can precipitate on the surface of the membrane, for example, or TOC, which can do some carbon fouling of the electrodes of some electrolyzers for the PEM1. So we can look really for each ion what type of impact we can have on the performances and the long-term operation of these systems. But we can see that those requirements are going to be a bit stronger in the future because, as our specialist said, no electrolyzer has ever been damaged by a water that was too good. So by meaning that to protect all these assets, which are crazy expensive, we need to work on what goes inside, which is the water. So now we know the amount of water, the quality, but how should we get to this quality? We can divide these steps into two categories. First of all, you will have the pretreatment because, of course, depending on the water you decide to work on, you will have different technologies that you have to put in series to reach this quality, right? So, for instance, if you start from groundwater, you might need only sand filtration and aeration to get rid of iron, manganese, and ammonium, stuff like that. For pre-treated wastewater and surface water, now we talk about a bit more complex technologies such as ultrafiltration, UV system, sand filtration, activated carbon to get rid of really components that you can find because this type of water behaves not in a very nice way over the year because it can vary from season to season or even from day to day. And then you have seawater, which you can use desalination, as Aaron just explained a bit earlier today. But you always have this second part, which is the polishing, what we call, which remains the same because from this pretreatment, you reach like some kind of drinking water quality from which you can work and develop this same ultra pure cubic meter of water that you need to produce the hydrogen. So it always goes by softening to remove the hardness from the water, demineralization by reverse osmosis, single or second pass, we can see that later, degassing to remove the gases, such as CO2, which can impact conductivity, which you want to remove. And then final polishing, either with electrodeionization, EDI, or mixed beds, which is like a resin technology. So all those technologies that I mentioned, they come with alternatives in each case, and with different selection criteria, such as CAPEX, OPEX, sustainability, footprint, or water consumption. So you can really optimize and design a system which is really made for your application and your electrolyzer itself. So if we start from the beginning with filtration activated carbon for particles, small particles, and free chlorine removal, now you switch to softening. And the alternative to that one is something called antiscalant, which is like chemical dosing. After that, you can switch to reverse osmosis to remove, again, salts, silica, TOC, and so on, up to 95, 99%. You can also have an alternative of switching to double pass, which is like getting a bit better quality. Then you switch to degassing, and the alternative to that is another chemical dosing, which is dosed upfront, the reverse osmosis, to convert the CO2 to bicarbonate so you can remove it with membrane-based technologies. And then you have the final polishing, which is important because this is where you reach the right quality for your electrolyzer, either by mixed bed or EDI. So through all these years of experience and those many systems, almost 100 systems that we have delivered to this day, we could develop some kind of standards, both for alkaline and PEM systems. But now we are also digging into the other ones, like such as anion exchange membrane or solid oxide technologies. But those are the two mains which we could develop really some good standard. So you can see here, for alkaline systems, it's always the same thing: softening, caustic dosing, double pass reverse osmosis, and from that you can already store this water, which is good enough to put inside of your electrolyzer. So you store it with a CO2 trap on top, and then you can go in your system that you can see there. For PEM electrolyzer, it's a bit different because, as again, we need a much stronger quality, so much lower conductivity. So we still have the softening as a pretreatment to protect the membrane, but also all the assets that are coming afterwards. Then we switch to membrane degassing, electrodeionization, and then we can store the water. And before it going back in the system of the electrolyzer itself, we can also add up a mixed bed polishing unit, which can really ensure that you get the right quality right at the inlet of the stack. Because the idea of here is to protect all those assets. They are really expensive ones, and making the extra effort on the pretreatment makes it really much viable on the long-term basis. So now I'm just going to end up not to go too technical and too theoretical, but on some case or example of solution that we have supplied. So this is, for instance, an example of 5 megawatt PEM solutions containerized. So you can see the advantage of having everything like very compact on a single frame unit with like softening, reverse osmosis, and mixed bed. On the other hand, we can switch to a bit bigger system, which was for a 20 megawatt alkaline system for Everfuel and in the high energy project in Denmark. In this case, we have had softening, coasting dosing, and DPRO as modular units, so they could really, there was not the typical problem that you have with containerized solution. So it didn't need to be so compact, so they could place those standard units more or less the way they wanted. And as a final example, I will use the latest one we have sold or we have put in service lately. It was for a 50 megawatt PEM system. This one was anti-scalene dosing, double pass reverse osmosis, which you can see DPRO, membrane degassing unit, EDI, electroionization, and a mixed bed for final polishing for this Siemens Energy of Kasoe project. So I'm not going to go too much in depth regarding the theoretical part of it, but we are exposing at the booth B11, so feel free to join us to go a bit more in depth or to see what we can do and what we can make so we solve your problems. And as a special surprise, we have a very nice article that was written by our specialist, again, Henrik Tekker Madsen from Denmark, that has already been published in a magazine. So feel free to come by, take your own that you can get a physical part, and feel free to reach out to us. Thank you.
Okay, nice job.
Do you have any question, maybe?
When you spoke about the water treatment technology options, there were numbers that they were on a slide, reverse osmosis, like 95% degassing, 70 to 80. What are those percentages referring to?
So the percentages is like the removal. So you can reach like 90% removal of these elements.
Contaminants.
And exactly. It's not about the efficiency. It's the efficiency in performances, but not the recovery.
And a question for you, if you
Certainly,
don't mind.
of course.
I was just lost in a match when you said like 1.4 cubic meters of groundwater, you get 1 cubic meter of Ultrapure. Like what's the remaining 0.4?
That's a great question. So it actually kind of follows along to your first question about the contaminant removal. So the contaminants that we're treating here, they have to go somewhere. They don't just disappear. So with reverse osmosis, fundamentally what we're talking about is a physical membrane separation type process. And so what happens is the minerals and the organics and whatnot that are in that water get concentrated into a reject stream. And as the source water becomes more challenging, you have to increase that reject stream ratio to the product water that you get out. So in a city water, tap water fed situation, you might get 75% of that water out as pure water, with the other 25% having a concentration of all of the minerals, the 95% of the minerals that are being rejected, okay? Whereas when you get into more challenging waters like recovered wastewater or especially seawater, you have to run those systems at a much, much lower recovery. So you might only get, for that same cubic meter that you put in with seawater, you might only get 30% of that out as purified product water, and you're sending 70% to drain with that concentration of all that salinity. So that's where that water is going. It either has to go to drain or it has to be disposed of some other way, and that's just a simple function of reverse osmosis technology itself. Certainly.
Any other question? Good.
Certainly, if you do have questions, please stop by our booth. Thank you all very much for joining us.
Thank you.